Teflon is pretty slick, so have a low coefficient of friction here. So that's the roughness factor. Notice it cannot have units. This is not friction. Some people write that as friction. That's not friction. That's only the roughness factor. So this is the coefficient of static friction. Notice that it depends also on the normal force. So that's the amount squeezed together in newtons or pounds or whatever force unit. So this is in newtons, that's in newtons, that's in nothing. You squeeze it together more, and you know you're going to get more resistance to sliding in a sense. Okay? So this affects it and the roughness. Okay? And let's explore that. So you pull, pull, pull until you're just about to slide. That's the equation that you use if you're given that condition. Okay? Roughness factor and amount squeezed together. And you can get that with anything. Let's do this guy here. I think I can pull that pretty nicely here. Let's do this one. So now I'm going to pull it to the side. If I squeeze, that squeezes it down, it's going to be harder and harder to slide, right? So that's the normal. The normal, if you squeeze things together, you sort of compress it. Think of your knuckles. As you squeeze them together, they're harder to slide side to side. You're getting more friction. It's not more rough, so the coefficient of friction isn't changing. But you squeeze it together, and it's harder to go side to side. That's why the normal, now remember, the normal is perpendicular. Friction's parallel to the surface, so different direction, certainly. But the amount of friction you get depends on that squeeze. Okay, so explore that. Another weird little thing. Okay, let's try this guy. Friction is 0. Friction is up along the cart surface. It's Fs until it's Fs max, and then it slides, and it's kinetic friction. So in terms of in terms of direction, you might say, hey, friction is a direction opposite the motion. That is not right. It's often right, but not always. Okay, watch. Friction is resisting the sliding, right? But wait a minute. Now if I push this way, what direction do those grooves engage? I mean, what makes this accelerate that way? The only thing touching this is the cart and those grooves. And so now, as I push this forward, I'm pushing those little grooves down in there into these grooves, and it makes it go that way. And so in this case, when I go like this, the friction, static, because it's static relative, this is moving, this is not moving relative to the cart. So there's relative static. It's friction between the two, and in this case, it's with the motion. It gets it started, right? So be careful. It's a little tricky. Friction is what's making that accelerate. Granted, my hand's there, but the direct interaction is between the cart and this object. Okay, so be careful. Static friction makes it move. Static friction makes it move. It's in the direction that it's going to be moving. And finally, we have kinetic friction. So if the object is sliding relative to the surface, not moving with it, then we have a very similar equation with a different coefficient of friction. The coefficient of kinetic friction, mu k, still the amount that the surfaces are squeezed together by whatever, for whatever reason, affects the friction. So the normal force, magnitude, not direction. This is magnitude, right? It's how strong it is. And this all goes into that big old soup of the method, and you work it out later. You can't do it in your head. This is opposite the motion of R relative to S. Static friction, the direction is tricky, and you're just going to have to think physics carefully. Okay? All right, so if, let's just explore that a little bit more. Take an object, and it is about to slide up, then the friction, the grooves between these, is going to be down. If it's about to slide down, the grooves are engaged such that the friction on this guy, R, is up the plane. If I pull up, the maximum I can pull with it not going, friction, static max, is down. If I hold it but I let it go a little bit, it's about to slide down, now friction is up. Pull strong, friction is down. Now friction is up. Friction is down. Friction is up. About to slide, which way? About to slide down, friction is up along the plane. About to slide up, static max is down along the plane. So you really have to pause and think about what case it is. And again, part A of a problem might be one thing and part B might be something else. So that's a pretty tricky little business, right? So coefficient, these are measured experimentally. You look them up in tables, or you give them, or you calculate them, which is how the experiment is done. You actually do the measurements and calculate them. Depends on the normal force. This is opposite the relative motion, kinetic friction. And it goes in with all the forces, and you work it out with Newton's laws. So that's a beautiful thing. Let's see here. I think we will stop with that for now. You'll explore that. I will real briefly talk about fluid drag. So this is solid to solid. This is fluid. Stick your hand out to the side of a moving car, and you know the faster you go, the more fluid drag you've got. You know the direction is opposite the motion through the fluid. You can do it through water as well. Faster you go, more drag. If you turn the same hand sideways, you're going to get less drag. So it depends on the orientation. It depends on the area. But again, the shape. All these factors come into this little coefficient of friction, B. The exponent can even be 1 in the simplest case, but it can depend on the speed, the fluid, the object, all kinds of things. So modeling this can be quite tricky. It's a good introduction to say that it's directly related to the speed to the first power through it, and with the direction opposite. So I think we've got it. Keep this as n, put it in, draw your free body diagram, choose which force of friction form applies, and let it work itself out. In this case, we do have an equation. In this case, we do have an equation. In this case, we don't, and here you don't need to be wasting your time with it. I think we're pretty good if you keep these grooves up here in mind. You'll be driven. Let's move on to our other forces.